Okay, so this is the outline for chapter 30. So we will talk about Faraday's law and also the Lenz's law. So Faraday's law is the third law in the Maxwell equation we learned. And actually, Lenz's law only refer to the negative sign inside the Faraday's law. So it determines it tells you how to determine the direction of the induced current or the induced EMF. And then we will talk about the induction and energy transfer, and also induced E field, which is also part of the Faraday's law. And then we will talk about the inductors and inductance, which is the third circuit element we will learn. So we already learned capacitor and also resistor. So in this chapter, we will also learn inductor. So in the coming two chapters, chapter 27 and chapter 31, we will learn some circuit analysis basic. So for easy students, they have a whole semester to learn about how to calculate the circuit, the resistive circuit, the RLC circuit. But here we only have two small chapters to talk about that. So maybe for you, it might be more difficult because we just spent too short time for that. But I hope you can still learn some skill which is useful for your future. At least most of you are engineering students, so all of you should know how to calculate ordinary differential equation, to solve ordinary differential equation. So here we'll briefly talk about it, and then later on, even though you are not trying to solving the circuit, you still need to solve ODE for other like a mechanical system or whatever you will learn later. And then we'll talk about the self-induction, which is the phenomenon of the inductor, and then RL circuit, and then energy stored in the magnetic field, energy density in the magnetic field, and then finally we talk about the mutual inductance. You can also regard it as a transformer. Okay, so here we first explain a first experiment. Okay, so this is the experiment setting. So a conducting loop is connected to a sensitive ammeter. Okay, so here we only have a loop. We don't have any battery. Don't have any battery. This is so-called a ammeter. Ammeter. The ammeter is to measure the current for the loop. Is to measure the current. MEASURE. Measure the current. Measure the current. The term sensitive here means it can measure a small current. So we call it a sensitive ammeter. So in this case, this current loop is, you can regard it just as a wire with an ammeter. So originally, without these magnetic things, it won't have any current at all. Okay, this is the basic setup. And then because there is no battery or no other source of EMF included, there is no current in the circuit. So the EMF here means electromotive force. In Chinese, it is called 电动势. Okay, so it's like a voltage difference, something like that. So however, if we try to move a bar magnet towards a loop, a current suddenly appears in the circuit. the current disappears when the magnet stops moving. Okay, so this is the strange things happening. So if you try to move the magnet bar close to it or even into it, then there will be current. But after the magnet bar is stopped there, but still really close to it, it still don't have any current. So yeah, and then if we then move the magnet away, a current again suddenly appears. So yeah, so if you try to move it away, then there will still another current, but the current is in opposite direction. Okay, so this is the first observation. So this circuit itself won't have any current because there is no battery, no EMF there. But if you try to move a magnet close to it, then there will be, it is like the movement will induce the current, and it is related to the direction of the current related to the direction of the movement. If you move close to it, then the current may be somehow in this direction. If you try to move away, the current is in the other way around. It goes in the other way around. Okay, so so this is the first observation, and then we try to do something else. So a current appears if and only if there is a relative motion between the loop and the magnet. The current disappears when the relative motion between them ceases. Okay, so it related to the relative motion. So which means that you can just fix this one on the table, and then you try to move the magnet close to it, then there will be, and during the movement of the magnet bar, then there will be current going through the loop. And you can also do this. You can try to fix the magnet bar there, and then you try to move this whole set relative to the magnet bar, and then there will still be current. So this is how relative motion means 相对运动. Okay, you can move this one and then make it stop, or you can stop this one and make this move. Then they still have relative motion. Okay, so and then we have further more detailed observation. It is like a faster motion of the magnet produces a greater current. Okay, so the current amplitude related to the speed of the motion. And then also, if the moving magnet north pole towards the loop, say clockwise current, then moving the north pole away will cause a counterclockwise current. Or if you just move a south pole towards the loop, then the current will be clockwise. And then moving away, then there will be a clockwise current. So related to the pole and related to the movement direction. And then moving the south pole to, this is actually this. Okay, so it relates to the speed and also the direction of the movement. I mean the current of the loop. Okay, so for the second experiment, we just don't use the magnet bar. We just replace the magnet bar by the magnetic dipole, because in the previous chapter we already know that they are actually equivalent. So actually we don't try to move it. We try to also fix this loop. We just place these two loops close together. The only difference is that we place a switch here. So here we can try to switch it on or switch it off. If we switch it on, then there will be current. And if we just switch it off, then there will be no current. So here we don't have any relative movement, but we try to make there is current or there is no current. If there is current, there will be magnetic field generated by this loop, like a magnetic dipole. If there is no current, then there's nothing. So for this experiment, okay, so we try to switch S to turn on a current in the right hand loop, the meter suddenly and briefly registers current. If the switch remains closed, no further current is observed. So if we then open the switch, another suddenly brief introduced current appear in the left hand loop, but in the opposite direction. So we try to switch it on and then remain it closed and then switch it off. It is somehow similar to the movement of the magnet bar. So we get induced current only when current in the right hand loop is changing and not when it is constant. So whether it generates current on the left hand loop related to whether there are any change of current or actually change of magnetic flux on this loop. Okay, so maybe we just stop here today. We will continue next Monday. Yeah.